All right, chapter 3. We're going to start chapter 3 with a little joke here, okay? What weighs more, a pound of gold or a pound of feathers?
Um, oh, I think I've heard this one before.
Oh, you have?
Yeah, it's a pound of gold.
No, 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 no. You've heard it before.
Oh yeah, I mean it's the same.
It's the same. That's right. Both a pound, right? A pound of gold and a pound of feathers. I remember hearing that joke as a kid. Somebody would say, what weighs more, a pound of gold or a pound of feathers? Sometimes they would say it wrong. And one time I heard it, what weighs more? Or maybe I said it this way. What weighs more, a gallon of gold or a gallon of feathers? What's the answer when you say it that way? What weighs more, a gallon of gold or a gallon of feathers?
Um, Gallon is unit of volume.
That's right. A gallon's a unit of volume. So, what weighs more?
The gold.
That's right. The gold does. If they both have the same mass, let's say a kilogram of gold or a kilogram of feathers, then they have the same mass. That's it. They both have the same weight, right? But if they have different volumes, then they're not going to have the same weight. Well, there's kind of a similar type of an issue associated with atoms. What weighs more, an atom of gold or an atom of helium?
An atom of gold.
That's right. They're not the same mass, are they? Atoms have different masses based on their um, number of protons and neutrons that they have. So here's gold right here, 79. All right. What is that 79 again?
Number of protons.
That's the number of protons. That's not its mass, is it?
No.
All right. So let's bring this down a little bit, bring it over here. Let's remember that if I say something like gold 79, that 79 is an indicator. Oops, wrong place. Try that again. Gold 79, if I put the 79 there, I'm not going to call it gold 79, but 79 there is an indication of the number of protons. But if I say gold 180, and that's what I would name it based on its mass, right? That is the number of protons plus neutrons, right? Protons plus neutrons is 180. 79 down here is just the number of protons, and again, that's on the periodic table, okay? So an atom of helium, what's the average mass of an atom of helium?
The average mass?
Yeah, that's what this number is here, right there, right?
Oh, 4.
That's right, 4. And we've done this before, so there we go. We have two atoms there, an atom of gold and an atom of helium, and they have different masses, okay? Now, we've always called those masses, or those units, those masses, those masses units. And it's been relative to the lightest thing, which is hydrogen. And that's how the periodic table started. They found the lightest, and all of these masses were units identified in terms of how many times heavier they were than the lightest thing, which was hydrogen. Okay. Later on, they changed the scale to use carbon 12, and they gave it a mass of 12, right? 12 units. So, thing to take home here is that atoms have different masses, right? And that what we're going to do is we're going to use a new term called the mole to identify how an amount of an atom, a given atom or a given material, an amount of something. All right. So the word mole becomes confusing to a lot of students, a lot of people early on. And I encourage students to replace that word with the term dozen whenever it's bothering them, whenever it's confusing them. Okay? So like if I say I have a mole of gold, a mole of gold. We've never heard that term. What is that referring to, a mole of gold? Well, if I replace that with the term dozen, if I have a dozen golds, right? What that means to us now is maybe 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the others in the background you can't see. This is a mole of gold atoms, 12 gold atoms, all right? Sorry, this is a dozen gold atoms. If I say a mole of gold atoms, and the abbreviation is just MOL, not very creative, but that's the abbreviation there. If I say a mole of gold atoms, instead of being 12, a dozen gold atoms is 12 gold atoms, it's this number, 6 times 10 to the 6.02. Let's try it again. 6.02 times 10 to the 23rd atoms. I can't draw that many, way too many to draw, right? And this, let's say, is 1 mole of gold. All right, 1 mole of gold. And the mass that that 1 mole of gold is going to have is going to be equal to the mass in grams of, or that number right there, 197, 196.9665, right? So this is going to be 197 grams of gold. So 1 mole of whatever your element you're after, or material you're after, is the mass, the average mass of that in grams. So that becomes a little bit helpful, and we'll talk about that moving forward a little bit. You can think of the mole as short for like 1 molecular unit. Now, in the olden days, they thought everything was molecular in nature. We know now that ionic compounds, how do they reside? Do you remember, Fred? How do you find ionic compounds?
Ionic compounds.
Yeah, like sodium chloride, remember? We have this conversation a couple times. So if I have something like sodium chloride compared to something like carbon dioxide, right? Which one of these is molecular?
Oh, carbon dioxide.
That's right, carbon dioxide is molecular. Sodium chloride is what?
Ionic.
That's right. Carbon dioxide is found like this. It's a little cluster, it's a little unit, it's a molecular unit. But sodium chloride is how?
Oh, I can't remember what you called that.
Right? We have a sodium and chlorine, and it goes off.
Oh, yeah, it's a lattice.
That's right. And it's not just in 2 dimensions, but it's in what?
Oh, 3 dimensions.
That's right. So I drew a 2-dimensional portion of it there, and this would go off in all dimensions here, going off, repeating sodium, chloride, okay? So that's what a 3-dimensional lattice is, and that's how you find ionic compounds. Just a little review there. But they didn't know that initially, and they called everything molecular for a while. But we know now, we can think of that term mole as trying to indicate 1 unit of a given material. So here's some examples of some moles. So here, this is 65.4 grams of zinc. And if we look at zinc here and find that it's 65.4, that's the mass. And so 65.4 grams of it is 1 mole of it, right? Here's copper. It's a wire, right? And it doesn't need to be in just a pile of dust like stuff. 63.5 grams of copper. Again, that's the mass there. And therefore, that many grams is 1 mole, 1 unit of it, okay, 1 molecular unit. You can have a mole of anything because, again, the word mole and dozen are used in similar ways. It's telling you how many units there are in 1 cluster of them. To kind of help us think about why chemists invented the mole, we're going to talk to you about the story of why the farmers invented the dozen. Now, this isn't a true story, but it's a helpful story to get you to think about the mole. All right. So in the past, farmers would sell their eggs. They would sell eggs at the store, and you could buy 1 egg, 2 eggs, 3 eggs, 27, 69, all sorts of eggs. But the farmers were losing a lot of money because they had to have special boxes that held their eggs. And if somebody wanted 6 eggs, they needed a box that could hold 6 eggs. If they wanted to have 13 eggs, they needed a box that would hold 13. And so they were losing money in boxes and having so many different kinds of boxes. And so one day they said, we're only going to sell eggs in units of 12, and we call it a dozen. So if you want eggs, you have to buy them in dozens. And so that they could buy just 1 kind of box and they were going back to being profitable again, right? Now that's not a true story, but you can think about when people made decisions to sell amounts of material in units, right? Same thing with paper, right? Paper is sold not usually by the sheet, but in reams. Pens often are sold in units, 200 maybe, something like that. Eggs in dozens. Sometimes donuts are sold in dozens as well.
You can buy a donut by itself.
Yeah, but you get the picture, right? Chemists needed their unit so that when I wanted to, for example, react, I wanted to use gold as an example. If I want to react gold with some chlorine, all right, and if I know I need 3 chlorine atoms for every gold atom, right, and I'm going to create AuCl3, all right, now I know how much gold I need to weigh out and how much chlorine I need to get to create my AuCl3. Try that again. Au plus 3 Cls forming AuCl3. Okay? This equation helps me. I recognize I need 1 gold for every 3 chlorines, and I'm going to make 1 of these AuCl3 compounds, right?
Okay.
So how much gold do I weigh out?
I don't know how much.
Well, I can use the periodic table and say if I weigh 197 grams of gold, and I need 3 chlorines. Each chlorine is what?
What's it say? 35.45?
Yeah, so 35.5 maybe. 35.5. That's 1, but I need 3 of those. All right. So 35.5 times 3, that's how many grams of this I'd weigh out. 197 grams of that. And then if I combine those together, I would have what we call the correct stoichiometric relationship, which is essentially saying the appropriate amount for each of these to be completely utilized to form this compound, right? And the law of conservation of mass would tell me how much gold chloride I should expect to get out, right? So let's do this math here, 35.5 times 3. All right, so this is 106.5 grams. We only need 3 significant digits, so it'll be really 107, but we'll just hold on to that for a little bit. And then the resulting mass between these, plus the 197, would be about 300 grams, maybe 303 grams of gold 3 chloride after these 197 grams of gold and 106.5 grams of chloride would react. Okay? So that is why we invented and why we use the term mole. Okay? Now, the likelihood of me wanting to perform a chemical reaction exactly in these ratios is generally not going to occur. I don't necessarily want to use that much mass of a given material and that much mass, right? I might want to just use a little bit less, right? But I can still use the same ratios. So, for example, 0.197 grams of this and 0.107 grams of the chlorine here, right? I could react that much gold and that much chlorine in those ratios, which are the same ratios as these, right?
Just 100 times less.
That's right. No, so 1,000 times less.
Yeah, 1,000 times less.
Just 1,000 times less, and I would get 0.303 grams of my product. Okay, good. Good stuff.